Alright, so I know what you're thinking. You're thinking, Nick, we're 5 episodes into this and we haven't done anything with the PIC yet. And well, good news, that's about to change today. We're going to be blinking an LED. To do that, I need to go over a couple things first. Mainly registers that control I/O with the PIC. So today we're going to be doing just simple digital input-output. Actually, we're only going to be doing digital output. So I need to show you how to set that up, but in order to do that I first want to show you what things you need to take into account in order to do that. So first things first, I thought it would be good to go over where you can get links to all the documentation I've been using, such as the data sheet for the PIC. So if you Google the PIC32MX250F128B, one of the first things that'll pop up on Google is this link. So it's directly on Microchip's website. So click on that and you'll get to this page, and then what you want is this documents. And of course you want the data sheet for the part, but the other thing that's going to come in handy when you're trying to learn how to use this thing, and that I've been finding really handy, is if you scroll down you'll get to code examples. Might be useful, but the things I've been using are these reference manuals, and they go over all the things that you might be interested in using your PIC for. So they go into oscillators, I/O ports, which is what we're going to be going over today, timers, we're going to be doing shortly in a future video, UART, anything that is useful on the PIC. So these reference manuals are great resource, but they are not specific to your part. I think they're just general to the PIC32, so you need to use them along with the data sheet to fully understand your part. So let's go over I/O ports. Well, a very, very limited scope on I/O ports today. Again, we're just doing digital output. So if you download the if you go down to this reference manuals and you get the I/O ports one, you'll get this bad boy. And just scroll down a couple pages and you'll get to control registers. It's really interesting to me how much this PIC can do with only 28 pins, and how it manages that is you can change what pins do, and so there's registers that go into controlling that. Today we're only concerned with 3 of those registers, and those registers luckily are these first 3. The tri-state register, or TRIS-X. This X is it takes the place of a letter. So the things we're going to be looking at in our examples that are coming up are TRIS-A and TRIS-B, and so those are the tri-states that control whether or not the port A pins or the port B pins are going to be inputs or outputs. So these TRIS registers control whether your digital pins are going to be either inputs or outputs, and they have a nice, luckily for us they did it in a nice way where if you want it to be an output, you set it to a 0, which looks like out, or O for output, and then a 1 for input, which kind of looks like an I. So that's an easy way to remember that. But today we're just going to be using outputs. So we're going to be setting a TRIS register at least one pin on a TRIS register to a 0. This is the port register. That's another one we need to take a look at today, and that is the actual values that are going to be on the pins. So obviously that's important for what we want to do today, which is drive an LED. So, and then lastly is this lat register. Now these lat and these 2 registers, lat and port, are very, very closely intertwined. A good general rule for them is you want to read from your port register. So if you want to know what value is on a pin, you want to read from the port register, but you want to write to the lat register. The reason behind this is a little confusing. It's one thing I did not understand very clearly when I was learning the PIC32 up at college. So I did a little bit of research and kind of figured it out, at least enough, hopefully, that I understand it correctly. I found this guy's website. It's electrosum.com, and the article is Read, Modify, Write Problem with Mid-Range PIC Microcontrollers, and it's by Lego George. Hope you guys can read all this, but he did a wonderful job breaking this down. At least hopefully I have a good understanding. And basically what it is, when you have your I/O ports that have to interface with the real world, you might get some capacitance that builds up on a pin. So in this example, what happens is when you want to do a read, modify, write, you read what value is on the pins, then you pull it into the microcontroller and modify the value, and then you want to write it back out to the pins. And how that happens on the PIC is it reads the entire port, so however many pins you have on your port, it's going to read them all in at once. Then it's into like an internal register. So that's this first step where it takes, hey, I've got all zeros on my pins. It reads them into the internal register. Then here, it modifies the individual pins that you want it to modify. So it reads all of them in at once, and then you modify whichever ones you wanted to. And then it's going to try and write to the output pins all at once. So it reads them all in at once, modifies individual pins, and then writes them all out at once. And the reason this is a problem is if you have a lot of capacitance out here, it might not change very quickly. At least not, it might not change quickly in relation to how fast the PIC is operating. So what would happen if you tried, well, let's just go through it. Let's say we wanted to change, so we just did this change where we changed this first pin from a 0, so we read everything in, changed that pin to a 1, and then said, hey, I want this to be, tried to write it back out to the pins. But let's say that this capacitor causes it to take a little while, so it doesn't change immediately. So like what he's trying to show here, I think, is it should be a 1, but maybe due to the capacitance it hasn't risen to a value where it would be interpreted as a 1. So a 0 accidentally gets written into the internal register, and then in this case we weren't modifying the same pin, we were actually trying to modify a pin clear over here, but since it incorrectly read in that what should have been a 1 but wasn't quite up to the whatever the balance point of the voltage was to read as a 1, it got interpreted as a 0, and since everything gets written back out at once, since it didn't read in a 1, now it gets written back out as a 0. So what happened was, in this first case, I tried to change this first pin from a 0 to a 1, but because of the capacitance on that pin, it didn't happen very quickly. But my processor's so fast that since I tried to modify a different pin on that same port quickly, it didn't get to a good enough voltage to be interpreted as a 1, so it got read in as a 0. Then I only modified this one with this incorrect interpretation over here, and then I wrote everything back out at once. So it, in a sense, nullified my original read, modify, write. So to get around this, what Microchip did was they added this lat register, which is what we've been talking about. And essentially what it does is it creates a buffer. And again, this is my own understanding of how this works. This could be incorrect, but this makes sense to me, and I'm pretty sure, hopefully I'm at least in the ballpark. So what it does is it gives you a buffer where the outputs on this lat B register are internal, so they're not coupled with external capacitance, which is what's going to slow it down. So what happens is you read in your port pins to the lat, and then those values get put into the internal register where they get modified one by one. Then they get dumped back out to, after they've been modified, they get dumped to the lat register. And then that lat register can get dumped, well, whatever's in the lat register gets dumped to the port register. But the advantage here is you have you have that physical decoupling with the external world from a register that's going to maintain what values will be on your output. So I really don't feel like I just explained that. I thought I had a better grasp on it. I guess I breezed through these pictures too quickly. I shouldn't have skipped steps, but let me see. Hopefully that made sense. Again, basically it just decouples the external world from something that's holding the values that should be on your output pins. Okay, so hopefully that makes sense. That's why in general you always want to read from the port pins, because those are the actual values that are on there right now. So even if it is taking long to change values, you want to read what's currently on there, because that's what you want to use, because that's what the external world's seeing, which is whatever your PIC's interacting with. But you want to write to the lat register, because that is not affected by the external world, and it will sync up with the pins eventually, independent of how long it takes them to charge. Because again, it holds the values that are going to be on the port pins. So hopefully that made sense. Let's get into doing some actual work. So I'm going to switch to... Oh, before I go into that, sorry, I need to go back to the data sheet. We're going to look at our pins real quick, because today we're going to be putting an LED on the the port A1 pin, which is identified as RA1, and that's right here on the schematic, or on the data sheet, sorry. And so that corresponds with pin number 3, so that's going to be 1, 2, 3 pins down. So I went ahead and made a little weird schematic that we're going to be using. So again, RA1 is a pin on port A that's the number 1 pin. So there's actually a 0 pin, and there's a 1 pin, and so on for how many pins you have. But today this is the circuit we're going to be building. So we're going to come off of our RA1 pin, then we're going to go into an LED, and then we have a current limiting resistor here with a value of 1K. I'm just using a junk diode that I got out of this random electronics kit. Hopefully you know all about device orientation, but if you have a new diode, it's going to have one lead that's longer than the other. That's going to be your anode, and that needs to go to the PIC, or if you're using it in a different circuit, that needs to go to the most positive voltage. And then the cathode's the shorter leg, and that's going to go to our 1 ohm resistor here, which is then going to go to ground. So I'm going to go ahead and set that up. It's nighttime here, so I'm using a lamp. Hopefully that's not going to be a problem. But okay, so I've got my LED here, and for me, my long leg, oh god, I keep blocking the light. My long leg's on the bottom right now, so that's going to go to pin number 3. Let me get a pen so I can count it for you. So we got 1, 2, 3. Okay, I'm going to go, long leg goes in that node to any other node that's not being used. Sorry, I know you're going to be getting a nice horrible shot there. Hopefully you can see what I did. I've got it in the 3rd pin over, and then over here it's going to that's really hard to see. It's going to a node that's adjacent to the other one. But so then we're going to go from there to ground. So join that up. Okay. And that's all the hardware we need to mess with today. So again, the long leg of the LED goes in the 3rd pin, goes to any node on the breadboard that's not being used. Then it shares that node with this 1K resistor, which then other side of that goes to ground. And I guess the ribbon cable's kind of in the way there. Hopefully you can see that. I know the lighting's not the best, but hopefully that'll work for you. Alright, my PIC kit is already plugged in and good to go. So I'm going to switch to desktop with board, and we're going to launch MPLAB X. Okay. I always kill the start page. It kind of looks cool, but I don't like having it open. So we're going to do a new project. Microchip embedded, standalone project. Good to go. Again, we're looking for that PIC32 family, and then scrolling down, PIC32MX250F128B. That's our boy. And then my debugger, it's going to be the PIC32, and I'm using the compiler that I had. Today we're going to do LED blink, something like that. Go ahead and smash it, let it do its thing. Alright, we're in. Now if you remember from the last video, don't forget to tell your PIC kit to power the chip. So we're going to go File, Project Properties, PIC32, no options again. Dang it. I don't know why this keeps happening. I'm going to unplug it, and then I'm going to plug it back in. See if that works. Come on. There we go. I really don't know why that happens. Okay. So, oh yeah. Sorry, that was a little fast. Project Properties from the File menu. File, Project Properties, PIC32, then go down to Power. Tell it to power the device. Leave it at 3.25, and we're good to go. Just to make sure everything's working correctly so far, I'm going to refresh the debug tool. Make sure we can get, target device found. Good to go. Alright, so now we're finally ready to write some code. About time, right? Okay, so we're going to go up to the source files. If you click on the expansion, nothing happens. That's because we haven't written anything yet. So we're going to right click, go to New. You won't have all this stuff probably. Go to Other, and then we're going to go Microchip Embedded, expand that, and go down to C32 compiler, and then hit this main.c, and rename this main, and hit finish. And here's our first file. This is a template, and this is just some microchip stuff. But here is the actual program, and that's all that's in this template right now, which is nice, and we actually aren't going to add too much code, believe it or not. So I guess I'll try and go over a couple things. This header library that gets included automatically is very handy. I'm going to be going over that in a few videos later on. I just looked down at my board and noticed my LED's blinking because I have the software preloaded. So I'll tell you what, I'm going to run this right now just so it stops blinking. Oh, and I'm missing, I don't have the board view on my OBS. I'm going to fix that for you too real quick. Hopefully that'll be fine. Okay. Yeah, hopefully that'll work. Okay. I hope that's showing. Oh, you know what? I'm going to move this over here since we're coding today. And let me get that a little better. Oh, whatever. It's fine. Okay, so my LED is off, and we're good to go. Sorry about that. Back to what we're doing. So, I lost myself for a second. Okay, first thing we need to do, if you remember, is set up these registers. Very first one we're going to set is the tris register, tri-state register, and because we want to set our pin that we just connected our LED to be an output. So in order to do that, here is all you need to type. Go down below this function prototypes and type in, oh sorry, don't do that up there. Go inside main, so inside this bracket, that's where you want to put it, and do tris A bits dot tris A1 is equal to 0, and that is setting the RA1 pin to be an output, because if you remember, 0 is an output and 1 is an input. Okay, next we're going to initialize that pin to be 0. I've heard that it's just good practice to get into that you always initialize your pins and variables to values that you know. That way everything starts up in a known state. So we're going to do lat A bits dot lat A1 equals 0. That's initializing RA1 pin to be low. Okay. Next we're going to delete this semicolon after the while loop, drop some curly braces in there, and then do lat A inv or lat A invert equals 0x0002, hit a semicolon. That's going to invert, I could have left it caps, but the RA1 pin, because if we turn it on and turn it off, that's inverting the pin, and then all we need to do to make it blink is wait a little bit in between switching it on and off. So let's make it wait a little bit, and how we're going to do that, oh sorry, up here add one more thing. We're going to declare a variable, so it's going to be an integer I. We're going to initialize that to 0, and that is just what do I want to say that is? It's a variable that's going to get incremented. So it's our weight variable, I guess. That's what I'll call it. And that'll make sense how it's getting used in a second. So down here we're going to go for I equals 0. That's the value we just created. That's the integer we just created, sorry. And for I less than a huge value, because remember the PIC's operating at a very fast frequency. So what we're going to do is crank out 40,000, and then I++. If you're not familiar with for loops, what this is doing is, oh sorry, let's finish it real quick and then I'll go into it. Go down, add your curly braces, and then I'm going to add a comment here that we're going to wait, do nothing. So what I've told this to do is, oh, I guess I'll break down this entire little loop here. I know, hopefully everybody knows what all this does, but just in case there's some real beginners out there, just to hopefully help you get involved with this, is while loops, anything that's inside their curly braces is going to execute as long as the condition in between the parentheses up here is true. In C, a 0 is false and anything that's not a 0 is true. So since we have while 1, this loop is going to execute indefinitely. So once our PIC gets up and running, whatever code's in here, it's just going to get executed again and again and again until the end of time, or until we lose power or the thing breaks. So what's inside here? Well, the first thing, we come in here and we invert our pin, which is going to make it blink if there was a pause in between those inversions. And that's all we're doing right here, is a pause. And how we're doing that is, we have our integer I. It starts at 0, and then it's going to increment by 1 at the end of this loop. If you're not familiar with for loop syntax, look that up. But this is just going to execute and increment I until it gets above 40,000. And so the PIC's going to be operating at a certain frequency, and this for loop's going to take a certain amount of time to execute. And since nothing's happening inside of it, it's essentially just like waiting. And this is a terrible way to wait, by the way, but just to get things up and running, that's what we're doing today. So here's our pause, and we're inverting it each time. And that's all the code we need. So we're going to come up here to this Run Main Project button. Go ahead and click that. It's going to go through some text here. Build was successful, and now it's going to try and put it out on the board. So hopefully I remembered everything. And it does take a second. I think the first time you build something, it takes longer than afterwards. So let's see what you guys can see. Hopefully you can see that the LED is blinking. I'll turn off the light. There you go. And why not? We'll go full screen just so we can see it in all its glory. Everything we've done up to this point just for that, just for a nice blinking LED, the hello world of the embedded world. But you know what? As simple as it is, it's still very rewarding. Okay, we'll come back here. So probably a few things in this code don't make very much sense to you. I'd imagine for some people this line's not going to make very much sense if you're very new to this. And this 02 or 0x0002, what is that? Essentially your lat register, it can be represented in a lot of different ways, but it's going to be, I think it's, what are they? I need to look it up before I go in and talk about it for sure, but it's either a 32 or a 16-bit register. And so you can represent that with binary numbers, so that'd be 0, 1, 0, 1, 0, 0, whatever the combination is, or you can represent it with hex, which is what I've done here. And so what I did was I knew, well, since the port starts at pin 0, so that would be RA0. RA1 is actually, so for example, if I had 0 here, that would be our RA0, and then here would be RA1. And actually it's the exact opposite, it's 0, 1, because RA1's an output and RA0, which by the way, on every reset, all your I/O pins get set to inputs by default. So, but anyway, it's actually this position in the register that's the one I'm interested in, and I represented that in hex with this 0x0002 value. I think the next video I'm gonna go into hex and binary a little bit and registers, and then also these commands probably don't make too much sense to you, but I'll probably tie those in because it's actually probably representing something similar to this with all this, with all these characters. And I'll show you how to look up where these things are defined, so where you can learn how to use them. But that's for a future video. I just wanted to get you guys up and running with this LED today. So sorry to make you sit through all that, but hopefully things made sense. Feel free to let me know if they don't, and I'll try to get back to you. But thanks for watching. Have a good night from my point of view at this time in the video, and hopefully it all worked out for you. Thanks.